We're now at the second video of this section, exploring more about graph algorithms. In the previous video, we looked at reversing a list. In this video, we'll learn about graph traversal and how to avoid list appending. Also, we'll look into topological sorting. A graph has a finite number of nodes, also commonly called vertices, connected via edges. Trees are special cases of graphs with additional constraints. There are undirected and directed graphs. We'll be looking at directed graphs, also known as digraphs. I will explain the terms as they come along, however, this website would help as a quick refresher or introduction for you. Have a look at this diagram. A list of pairs will be used to model these directed graphs. The second element of the pair should be a successor of the first. For example, the M nodes' successors are N, P, O. The previous graph is modelled in the code, which I'll be showing you next, where each edge is denoted by a pair, and the graph is a list of such pairs. Now, let's create the graph and define the list of pairs first. The first pair is MN. The next pair is MO. The third one MP, and so on. As you click Enter, you obtain the graph with different pairs representing the vertices. Now let's define the sucset method, which collects the set of successors of a given vertex. Define sucset, a colon string, G colon string, and then define the list. Next, we write the case clause. We use an if condition in the second case, and the third case, xs sucset, a comma xs. Here's how the sucset method is formulated. Now let's try out the sucset method. Sucset m, graph. This is a pretty simple method. We traverse the graph and check the first element. If it equals the argument vertex, we collect the second element, which is the successor. Let me show you an idiomatic way to write the previous method. We use graph filter for m. Let's try it in a different way. This method is an important building block for the upcoming algorithms, as you'll soon see. Now, let's move on to learn about graph traversal. Graph traversal is the process of visiting each node in the graph. There are two strategies, either a depth-first traversal or a breadth-first traversal. The name depth-first indicates that a node's children are visited before its siblings. On the other hand, in a breadth-first strategy, all the node's siblings are visited first and then its children. In either traversal, we visit a node only once. We'll be implementing a depth-first traversal. Implementing the breadth-first traversal is left as an exercise for you. Now, check out the figure on your screen. As you can see in the diagram, we start the traversal at node M. This node has three children, its successors, N, P, O. We visit the node N first, and then the N node's child, namely Q. The traversal always visits children first, so when we're at Q, we go to S and R. The other way, that is, visiting R and then S, would also work. As R and S have no children, we return to Q, and then to N, and finally to M. The traversal next visits P, which is the second child of M. Now, when we start looking at the P node's only child, that is Q, we find that it was visited earlier in the traversal, so the Q node is skipped. Lastly, O is visited, and when at O, we find its only child, R, has already been visited, so it's skipped. This completes our traversal. Let's write the traversal algorithm code. First, we define depth first, an initialize string, and define graph list. Now we define a helper function depth f with list of nodes, nodes visited, and nodes matched. As we did previously, now we need to define the cases. The first case, nil visited. The next case, with an if condition for the nodes visited. In the third case, we use the sucset method. Now define a variable named result to display the result of the depth-first search. So, here's the result of our depth-first algorithm. Now let's try out this method for m in our graph. This method implements the algorithm outlined in the previous code. We use an internal helper method, depth f. This method is the real workhorse function. Note that the input graph is never modified, however it needs to be referenced. We could have written just one method, but it would require passing the graph as an argument. Is there a way we could stay away from passing the same argument, but at the same time have it in the scope so it could be referred to? Closures do just this. Let's take an example for this. First, define a variable, for example m, and we initiate this to a value of 10. Next, define the call and print method, which will take a function as an argument. It calls the function, passing in the first argument and prints the result. After this, we write the print statement to display the values. Here we have the call and print function as we defined. Now it's time to use it and pass the values. Call and print say the value of t here is 5, where t is an integer greater than or equal to t plus m, dot toString. We get the output as 15. Let's do it again for t minus m. As you can see, we have a different output this time. Here t is 5 and m is equal to 10, so it returned 15 for the first time, and 5 minus 10 gives us minus 5. So our call and print function worked as expected. Note the argument t:\int, t plus m dot toString, which is an unnamed function literal. For the function literal, the variable m is in scope. As far as a literal is concerned, m is a free variable and t is a bound variable. This explains why the variable g is in scope for the depth_f method. We prefer to keep the depth_f method private, thereby hiding its implementation details. We use visited, a list of nodes, to keep track of already visited nodes. Note that we use list prepending to add node x to the visited list. However, the visited nodes are saved in reverse order of visitation. We can fix this in a minute though. This case clause is hit when we have no more edges to traverse. In other words, reaching here means the traversal is complete. We just return the visited list. This clause matches when x is a member of the visited list. This tells us to skip x as it was visited already in an earlier traversal and got added to visited. So we just continue our traversal with the remaining node elements. This is an interesting clause, which is matched when we encounter the node x for the first time. We take the children of x via a call to the succset method. We prepend this list so the children visited before xs, the siblings, which makes this traversal depth first. Let's have a refresher showing the list method double plus operator in action. List 1, 2, 3 plus list 4, 5, 6. The first list of elements appears before the second list elements. The enclosing function depth first is just a shell. Its job is to present a convenient public interface to the caller. It converts the initial traversal node into a list with one element. It sends an empty list for the second argument of the depth_f method. It also reverses the result, creating the reversal introduced by the prepend operation. It's time to learn how to avoid list appending. You would know how adding two lists works. Here's a diagram showing list additions. The first list is copied, and the second is structurally shared. For every node's children list, we pay for this copying. Could we do better, thereby avoiding this expensive list addition? Let's check out the code for this. Define the depth first method. Also define the helper function depth_f, as we did previously. Now, we write the case clauses. The first case, nil visited. Next case, with an if condition for the nodes visited. We use the succset method in the else statement, and define the result. Here's how our depth first method is formulated. This slightly complicated version avoids the list append. The only change is how we handle the case of visiting a node for the first time. We make use of Scala's if-else statement, which is an expression. It's time to use some values and try out the function. We define the value for variable x, say 10. Value k is equal to if x greater than 25 else 30. Similarly, for less than 5, 20 else 30. The point to note is that if the condition is true, the if body is evaluated, and its value is the result of the entire expression. If the condition is false, the body of the else clause is evaluated and assigned likewise. We use this feature and express the algorithm differently. We go and visit the children of X right away and then continue with the earlier nodes, thereby avoid having combination of any list. OK. Now, let's step ahead and learn about topological sorting. Topological sorting is a sorting algorithm for sorting tasks as per precedence. Certain tasks, for example, need to happen before other dependent tasks. The compile step needs to happen before we run the code. Saving the source code needs to happen before we take the compilation step. We usually shower before we dress, and not the other way around. Task precedence is central to build tools, such as Make or Maven. For example, you can't run tests after you've deployed the app. Here's the routine of a typical office day, as well as an off day. There are two linear sequences of events here. The first shows chores of a typical office day. The second shows events of an off day. Finding such linear sequences in a graph is topological sorting. Now, let's write the code for the graph defining these activities. Define a variable gr work with the list containing different pairs like get up, shower, shower breakfast, breakfast dress, and so on. So here's the list of activities we just defined as string. With a small change to the depth first one method, we get the sorting. We define top sort with the glist. Next, we define the sort method with list of nodes, nodes visited, and nodes matched. Of course, we need to give the case clauses, nil visited. In the second case, we use the if condition for the nodes visited. Val start comma underscore is equal to g.unzip. The result is equal to sort, comma, start comma list. And here's our top sort function. What is the change? The current node X is just prepended to the recursive result of topological sorting its successors. If X is already visited, the case is as before, we just skip it. If X is seen for the first time, we topologically sort its children and prepend X to the result. Let's see this in action. Top sort gr work. The task precedence is correctly computed. Let's try it again the other way round. Here is another run with the graph, which is just a list of pairs reversed. Again, task precedence is correctly computed. Great! In this video, we saw a few more examples to implement graph algorithms. In the next video, we'll learn about cycle detection.